Hi, I'm Qayyum, CEO of OORB. Today we're looking at how we make deploying robots much faster and more reliable. Let me show you. The example is collecting training data for those two SO11 arms, starting with the bimanual packaging task. Every demonstration like this becomes an episode, and every run you'll see in this demo, this one included, is being recorded by our product. Here's what it looks like. You control it via your terminal, you can script it via an SDK or through the TUI. As you can see, it's running locally. And setup only takes a couple of minutes. So here I pointed at the right workspace, directories. It understands and tracks everything around it with the code, the calibration, dependencies, hardware, and environment. I can also pick my inference target, for example my local Jensen, or a cloud machine. The interfaces screen probes the machine live, platform, the OS, Rust version, and capture status. Now I start tracking my experiments, and you'll watch the tool tell me exactly what's going on in just about 10 seconds. Capture is automatic. Once the robot is enrolled, I can also call it manually. And here's every run I've ever recorded. The experiment's table, every episode has its label, duration, message count. Your code stays in Git, the recordings are in standard formats like mcaps and rustbacks, middleware agnostic, hardware agnostic, and native integration with Foxglove and rerun. So it sits next to your stack, it doesn't replace it. Let's open the experiment, either manually via one command that records everything, or automatically. It takes a second to do the regression diff, then it loads in the browser. I get an overview of everything the robot interacted with, and a summary of what to focus on. It didn't just save the data, it saved the exact code commit, the package versions, the calibration files as they were at that moment, the hardware, the frame rates, the run carries its whole context. To show the product's capabilities, we also fine-tuned a Pi 0.5 model on a different task. Same rig, but stacking rings on a peg. And watch. It tries to do the task under the conditions it was trained on in the dataset. Now, if the environment changes in an untracked manner, or someone pushed an engineering decision it was never trained on, same code, same calibration, same task, and look at it. It's performing worse. The grasp is falling apart. If you work with learned policies, you've seen this. And you know the bad part isn't the failure. It's actually the expensive question on how do you prove to yourself it was the lighting, and not one of the other 10 things that could have changed. So I select the good run and the bad run, and I open a diff. And here's the overview. All 8 layers. Some of them are green with 0 flags, which are 2 really clean runs side by side. And in this example, we have an identical calibration and code, but the dependencies are flagged. Since every episode carries its camera streams, here are the 2 scenes side by side. You can see the change that happened yourself if you go to the charts. These are the joint trajectories to overrun progress, one A in blue and B in pink, and you can watch the arm diverge. The right wrist roll drifting about 40 degrees. The behavior is the only thing that changed. And of course, there's a lot more in this report. Per field deltas, topic volume tables, every joint over time. I'll scroll through so you get a sense of the scope. Now we have the suspects eliminated and the cause isolated in 2 clicks. One more, because not every failure is just the environment. For example, there's calibration drift. So I'll move one homing offset by 50 ticks, the kind of thing 6 months of wear and tear does silently. And we run and compare, and we see a high severity. Calibration, the exact file, the exact joints, old value and new value. And another one, for example, of a dead sensor. So by unplugging one of the cameras and running again, you can see the tool detecting this with high severity with the dependencies going silently, and the exact topic, the exact run it disappeared in. And of course, code. So someone committing a change between runs and comparing shows us medium severity, the code vector, and here's the hash. And one detail I really love, the same hash is right here in my GitHub history. So the run record and the code record line up one to one. These are my runs from the past few weeks, daily up sessions, policy attempts, tests after rewiring. And an honest question, who on your integration, triage, or test and deployment team remembers what state the system was in, especially across different clients and environments? It's really hard. On a real team, this is thousands of runs a year, across many deployments, and all that context just evaporates. It does not have to, because it's all recorded. So I mark one known good run as the baseline, and certified checks every run against it. And there's the number everyone keeps asking robotics teams for, and one of our biggest modes, comparing across thousands of experiments and capturing all of this context. So you can see the success rate with a real confidence interval driven by a deterministic statistical model, where you can see that 70%, 10 runs, and every failing run listed with its causes and calibration changes, without me having to open a single log or write a single test script. And coverage answered the other question. Across everything we ever ran, which conditions did we actually test? So the gaps you're seeing are blind spots, visible for the first time. This is the layer we're scaling to fleets. When a customer asks how reliable a robot is, this is an answer, not a feeling. I can also take the real run and replay it in Isaac Sim from this episode. So the tool builds a real to sim package, the recording, the robot model, and the stream mapping. It validates it and shows me where it can run. I can of course launch it and continue my development in my sim environment. So that's it, applied to one real rig. Every run recorded with its context automatically. Any change explained in 2 clicks, and the whole history turned into numbers you, your team, your seniors can stand behind. And we think every team deploying robots ends up needing this layer, the same way every software team ended up needing version control and CI. So we're working with various pilots today. And if you're deploying robots too, I'd love to hear what you'd point this at. Thank you so much for watching.